In everyday life, we see some objects at rest, and others in motion. Birds fly, fish swim. Blood flows through veins and arteries, and cars move. Atoms, molecules, planets, stars, and galaxies are all in motion. We often perceive an object to be in motion when its position changes with time. However, there are situations where the motion is inferred through indirect evidences. For example, we infer the motion of air by observing the movement of dust and the movement of leaves and branches of trees. What causes the phenomena of sunrise, sunset, and changing of seasons? Is it due to the motion of the earth? If it is true, why don't we directly perceive the motion of the earth? An object may appear to be moving for one person and stationary for some other. For the passengers in a moving bus, the roadside trees appear to be moving backwards. A person standing on the road side perceives the bus along with the passengers as moving. However, a passenger inside the bus sees his fellow passengers to be at rest. What do these observations indicate? Most motions are complex. Some objects may move in a straight line, others may take a circular path. Some may rotate and a few others may vibrate. There may be situations involving a combination of these. In this chapter, we shall first learn to describe the motion of objects along a straight line. We shall also learn to express such motions through simple equations and graphs. Later, we shall discuss ways of describing circular motion. Describing motion. We describe the location of an object by specifying a reference point. Let us understand this by an example. Let us assume that a school in a village is 2 kilometers north of the railway station. We have specified the position of the school with respect to the railway station. In this example, the railway station is the reference point. We could have also chosen other reference points according to our convenience. Therefore, to describe the position of an object we need to specify a reference point called the origin. Motion along a straight line. The simplest type of motion is the motion along a straight line. We shall first learn to describe this by an example. Consider the motion of an object moving along a straight path. The object starts its journey from O, which is treated as its reference point. Fig 8.1. Let A, B and C represent the position of the object at different instants. At first, the object moves through C and B and reaches A. Then it moves back along the same path and reaches C through B. The total path length covered by the object is OA plus AC, that is 60 kilometers plus 35 kilometers equals 95 kilometers. This is the distance covered by the object. To describe distance we need to specify only the numerical value and not the direction of motion. There are certain quantities which are described by specifying only their numerical values. The numerical value of a physical quantity is its magnitude. From this example, can you find out the distance of the final position C of the object from the initial position O? This difference will give you the numerical value of the displacement of the object from O to C through A. The shortest distance measured from the initial to the final position of an object is known as the displacement. Can the magnitude of the displacement be equal to the distance traveled by an object? Consider the example given in Fig 8.1. For motion of the object from O to A, the distance covered is 60 km and the magnitude of displacement is also 60 km. During its motion from O to A and back to B, the distance covered equals 60 km plus 25 km equals 85 km, while the magnitude of displacement equals 35 km. Thus, the magnitude of displacement, 35 km, is not equal to the path length, 85 km. Further, we will notice that the magnitude of the displacement for a course of motion may be 0, but the corresponding distance covered is not 0. If we consider the object to travel back to O, the final position coincides with the initial position, and therefore, the displacement is 0. However, the distance covered in this journey is OA plus AO equals 60 km plus 60 km equals 120 km. Thus, two different physical quantities, the distance and the displacement, are used to describe the overall motion of an object and to locate its final position with reference to its initial position at a given time. Uniform motion and non-uniform motion. Consider an object moving along a straight line. Let it travel 5 m in the first second, 5 m more in the next second, 5 m in the third second and 5 m in the fourth second. In this case, the object covers 5 m in each second. As the object covers equal distances in equal intervals of time, it is said to be in uniform motion. The time interval in this motion should be small. In our day-to-day life, we come across motions where objects cover unequal distances in equal intervals of time, for example, when a car is moving on a crowded street or a person is jogging in a park. These are some instances of non-uniform motion. Measuring the rate of motion. Look at the situations given in Fig 8.2. If the bowling speed is 143 km/h, 1 in Fig 8.2, a. What does it mean? What do you understand from the signboard in Fig 8.2, b? Different objects may take different amounts of time to cover a given distance. Some of them move fast and some move slowly. The rate at which objects move can be different. Also, different objects can move at the same rate. One of the ways of measuring the rate of motion of an object is to find out the distance traveled by the object in unit time. This quantity is referred to as speed. The SI unit of speed is meter per second. This is represented by the symbol ms, 1 or m/s. The other units of speed include centimeter per second, cms, 1, and kilometer per hour, kmh, 1. To specify the speed of an object, we require only its magnitude. The speed of an object need not be constant. In most cases, objects will be in non-uniform motion. Therefore, we describe the rate of motion of such objects in terms of their average speed. The average speed of an object is obtained by dividing the total distance traveled by the total time taken. That is, average speed equals total distance traveled by total time taken. If an object travels a distance s in time t, then its speed v is v equals s by t. Let us understand this by an example. A car travels a distance of 100 km in 2h. Its average speed is 50 km/h, 1. The car might not have traveled at 50 km/h, 1 all the time. Sometimes it might have traveled faster and sometimes slower than this. Speed with direction. The rate of motion of an object can be more comprehensive if we specify its direction of motion along with its speed. The quantity that specifies both these aspects is called velocity. Velocity is the speed of an object moving in a definite direction. The velocity of an object can be uniform or variable. It can be changed by changing the object's speed, direction of motion, or both. When an object is moving along a straight line at a variable speed, we can express the magnitude of its rate of motion in terms of average velocity. It is calculated in the same way as we calculate average speed. In case the velocity of the object is changing at a uniform rate, then average velocity is given by the arithmetic mean of initial velocity and final velocity for a given period of time. That is, average velocity equals initial velocity plus final velocity by 2. Mathematically, average velocity equals u plus v by 2. Where VAV is the average velocity, u is the initial velocity and v is the final velocity of the object. Speed and velocity have the same units. That is, ms, 1 or m/s.